Hello all. Today we are going to study a linear data structure array. Many a times we have to work with similar objects which can be maintained with the help of different variables in a computer program. But there is an efficient way to handle such a scenario with the help of linear data structure known as arrays. For example, if we have to store marks of 10 subjects, then we may declare 10 variables for each of the 10 subjects. Or we may declare a single array with size 10 as it is shown here. Its name is marks, and within the square brackets we have to specify the size. So here we have to store marks for 10 subjects. So we have specified 10. Arrays are one of the simplest and easy to use data structure. With the help of arrays, one can assign a single name to a collection of variables of single type. For example, here we have actually declared 10 variables, each of type float, that can be accessed under a single name marks via different index values ranging from 0 to 9 or 1 to 10 depending upon the language being used for implementation. In a similar way, one can have an array of any other primitive data type or user defined data type. That means we may have an array of already available data types, or we may have arrays of structures or classes which we have declared, that is user defined data type. Single and two-dimensional arrays are very common, though one can have arrays with multiple dimensions as well. Arrays can easily be traversed, searched, as well as sorted. So, they are frequently used in applications where one is handling relatively permanent collection of data, that is, changes either in the size of the data or within the data are not so regular. As far as the storage of arrays is concerned, then array elements are always stored in continuous memory locations. For example, let's say we are using a system where an integer data type takes 2 bytes of memory storage. Then, the moment we declare int student4, that means continuous memory to hold 4 integers gets allotted by the system. Here, an integer is taking 2 bytes. So, 8 bytes in continuation gets allotted. First 2 bytes is for the first element, that is element at index position 0. Next 2 bytes are used to store element at index position 1. Then comes the element at index position 2, and last 2 bytes out of these 8 bytes will be used to store the element at index position 3. So accordingly, we have marked these things in the figure. This is student 0, then student 1, then student 2, and finally student 3. Similarly, if we declare an array of floating point, say marks here, of size 3, and assuming that the floating point variable needs 4 bytes of memory storage, then in all 12 bytes in continuation will be allotted to store elements at index positions 0, 1 and 2 respectively as is shown here. Talking about 1D, then storage is easy to understand. But in case of two-dimensional array, which we usually visualize in the form of a matrix, the storage is bit different. The array elements in case of two dimension don't get stored in the way they are visualized. That is, they are not stored in the form of a matrix as is shown here. Instead, there are two possible ways to store the two-dimensional array, either the row first or the column first. For example, here we have declared a two-dimensional array named marks with 3 rows and 5 columns. So, the two possible ways to store this array are: first, we store row 0, then row 1, then the last row, that is row 2. Or we work with columns, that is column 0, then column 1, then column 2, column 3, and lastly the column 4. The same is visualized here. As we know, the first index represents row and second index represents the column. So, if we work row wise, then it is known as row major order, and all the elements lying in the first row are identified with first index as 0. So here we have 5 elements present at row 0. Then next 5 elements lying in the next row will have 1 at the first index. So accordingly, we have next 5 elements, and last 5 elements are from the last row. Here we have only 3 rows. So the first index comes out to be 2 for the last 5 elements. So in this way, the two-dimensional array elements get stored following the row major order. Another way that can also be used to store the elements of two-dimensional array is using column major order. Columns are identified using second index. So, first column elements are those with second index as 0. So, here we have 3 elements lying in the first column. Then comes next 3 elements of second column, which can be identified with the presence of 1 at second index position. Similarly, next we have all the elements from third column, then comes all the elements from the fourth column, and lastly there will be 3 elements from the fifth column, which can be identified with the presence of value 4 as the second index. Basically, serialization of array is to be done by considering array indices in lexicographic order, so as to store array with any number of dimensions continuously in the system's memory. Here we have only discussed the two-dimensional array, but higher dimension arrays, they are also possible, and all the elements of those arrays will be stored continuously in the computer's memory with the help of serialization. After looking at the ways to store array elements, next we see how to get the address of a particular element of an array with the given index. We start with one-dimensional array and then we work with two-dimensional arrays to compute address of an element using row as well as column major order. Let A be a one-dimensional array, then to find the address at which element at index position I is stored is given by this formula. B plus W times of I minus LB, where I minus LB is the number of elements to be skipped. Here LB is the lower bound of the index. If it is not given, then lower bound should be taken as 0. I is the index whose address is to be computed. B is the array's base address, that is the address of the first element of an array, and W is the number of bytes required to store a single array element. For example, let's say we have an array of size 6. Here 1, 2, 3, 4, 5, 6. They are simply representing the contents, and the index values, they are represented within the square brackets. So here we have an array of size 6. Then B is the address of the first element, which here is equals to 100, and W is the number of bytes to store a single element, which is equals to 4 in this example. Now, if we need to compute the address of element at index position 0, then it's nothing but the base address only. So here we have B equals to 100, W equals to 4, and lower bound, it is not given here, so we have to take it as 0. Simply put these values in the equation, you will get the answer with I equals to 0 for the first element. In a similar way, one can compute the addresses of remaining 5 elements in this example. Everything will remain the same. We just have to update the index whose address has to be computed. Accordingly, addresses of corresponding elements in this example come out to be 104, 108, 112, 116 and 120. If we consider a character which needs a single byte of storage and base address given as 1200, then the corresponding addresses for elements stored at index positions 0, 1 and 10 can easily be computed using the same formula. Here also lower bound, that is LB, has to be taken as 0 as it is not specified. Base address B is given as 1200, and since we are dealing with characters, so number of bytes required to store a single element, that is W, it has to be taken as 1. By putting different values of I as 0, 1 and 10, we get corresponding addresses as 1200, 1201 and 1210. The required information may be provided in a variety of ways. For example, here lower bound for index is given as 5, and instead of base address, we are provided with the address of element at index position 5 and it is equals to 1200. The number of bytes required to store single element, that is W, is given as 4 and we have to find the address of element at index position 8. So again, using the same formula, we can continue. We have to find the address of A8 and we are provided with lower bound as 5 and its corresponding address is also provided as 1200. So, in place of capital B, that address will be used, that is 1200. And final answer comes out to be 1212. That is, element at index position 8 is stored at a memory location starting at 1212. Now we are taking the last example for the one-dimensional array address computation. Here, the base address of an array B is 1020. The allowed indices are varying from 1300 to 1900. Kindly note we are not provided with the size of the array B. Instead, we are provided with the lower and upper bound on the array indices, that is 1300 and 1900. Thus, lower bound is given as 1300. Memory size used by each element is given as 2 bytes and we have to find the address of B 1700. Thus, in this example, base address B is provided as 1020, W it is given as 2, I we have to compute the address of index 1700 and lower bound it is provided as 1300. So after solving the equation with the given values, the final answer it comes out to be 1820. Basically, the complete information can be given in any form. You just have to put the formula correctly to get the answer. Next, we have to start with the address computation in two-dimensional arrays. Again, we have to work with a formula. So let's try to understand the same first with respect to row as well as column major order. So let's say we have a 3 cross 4 two-dimensional array and we have to find the address of element 10 which is stored at index 2, 1, that is second row and first column. If we work with row major order, that is storing data row wise, then in order to reach the element 10, one has to skip 2 rows completely and then after reaching the third row, one element will also be skipped to finally reach 10. On the other hand, if data is stored column wise, that is column major order, then in order to reach 10, we have to skip first column completely, that is the three elements 1, 5 and 9. After that, two more elements will also be skipped to finally reach 10. Now, we try to frame the required equations in each of the two cases, that is row major and column major order. Before that, let's note a few terms. Let we have an array A with m rows and n columns. Since there are two dimensions, so there will be two lower bounds associated with both of them. that is LBR for row, that is lower bound for rows, and LBC for column, that is lower bound for column. If LBR or LBC they are not specified, then assume them to be 0, as we have done in case of one-dimensional array. Again, W be the number of bytes needed to store single element of an array, and B is the base address of the array. Then if we talk about row major order, then the equation will remain the same. That is base address plus width of a single element, that is the number of bytes required to store a single element, multiplied by the number of elements to be skipped. In this particular example, in order to reach 10, we have to first skip 2 rows as is given by the first index. So, we have written 2 minus 0, where 0 is the lower bound for this index, as it is not given, so we have to put it as 0. This value, that is 2 minus 0, has to be multiplied with the total number of elements in each row, which will be equals to the number of columns. So here we will have 4, as there are 4 columns in the given matrix. After skipping rows, we may or may not have to skip a few elements. For that, we have to look at the second index. Here it is equals to 1. So we will add this term, that is 1 minus 0 here. Again, 0 is representing the lower bound for columns. So this is for the specific case. If we generalize this, then to get the address of the element at index position I and j in row major order, we have to first skip I rows. So we have I minus lower bound for rows multiply with the number of elements in each row, that is number of columns. So this term has to be multiplied with n, as it is representing the number of columns here. Now we have to add the number of elements to be skipped, that is j. So for that we will add a term j minus lower bound for columns, that is LBC. So with the help of this formula, we can get the address of element Aij using row major order. On the other hand, when we work with column major order, the formula varies like this. To get the address of element at index position 2, 1, we have to first skip first column completely as is given by second index. So we use 1 minus 0 for that, as lower bound for column is not given. Then this term has to be multiplied with number of elements in each column, that is nothing but total number of rows, which here is equals to 3. After reaching the required column, we have to skip 2 elements as is given by first index. Therefore, we will finally add 2 minus 0 to this term, where 0 is again used for lower bound for rows, which is not given here. So again, this is a specific case. We will generalize this now. So to get the address of element at index position I, j in column major order, we have to first skip j columns. So j minus lower bound for columns multiply with the number of elements in each column, that is number of rows. So this term has to be multiplied with m as it is representing the number of rows. Now we have to add the number of elements to be skipped, that is I. So for that we will add a term I minus lower bound for rows, that is LBR. So in this way one can find the address of element at index position I, j in column major order. Here also, if the number of rows and the number of columns are not given, then the same can be computed using the corresponding upper and lower bounds as is shown here with the help of these two equations. Next, we will see to a few examples where we have to compute the address in case of two-dimensional array. An array of size 5 cross 5 is given. Each element needs 4 bytes of storage. Base address is given as 49 and we have to find the address of A4, 3 using row major order. So the formula to be used is written here, that is the formula for row major order, and the values given are B equals to 49, W equals to 4, M and N are equal to 5, I equals to 4, J equals to 3 and lower bound for row as well as column is 0 as nothing is specified. On solving the equation with the given values, answer comes out to be 141. Now the next example. Here we are provided with lower and upper bounds for both the dimensions. The memory requirement for each element is 1 byte. Base address is provided as 1500 and we have to determine the address of x0, 20 using column major order. So we have to use the corresponding equation, that is the equation for column major order. Here we need the total number of rows only, that is m. It can be computed using the formula upper bound minus lower bound plus 1. So m comes out to be 26. Then base address B, it is given as 1500, W is equal to 1, I is 0, J is 20, lower bound for row is minus 15, that is LBR, and the lower bound for column, that is LBC, it is given as 15. Again, when we solve the equation using these given values, the address of x0, 20 comes out to be 1645. Now, this is the last example for this session. We are provided with the address of element A4, 8 as 4142. Bytes per element of an array is 2 bytes. Direct values of number of rows and columns are not given. So we will compute them using the provided lower and upper bounds as we have done in the previous example. We have to compute the address of element A0, 0. It is given that elements are stored in row major order. So the formula to be used is as shown in the slide. The given parameters are W equals to 2, lower bound for row is -4, lower bound for column is -2, number of rows, that is M, it comes out to be 6 plus 4 plus 1, that is 11, and number of columns will be 12 plus 2 plus 1, that is 15, and address of A4, 8 is 4142. One can solve it in any way, but here we will first determine the base address and then we will compute the address of A0, 0 using A4, 8 as 4142 and the given values. The base address is computed as 3882. Now B equals to 3882 and we have values of all other parameters. So solving the equation for row major order using I and j equals to 0, we will get the required address of A0, 0 as 4006, that is 4006. In this way, you can get the address of any element either in one-dimensional array or in two-dimensional array, provided all the required information is given to you. So with this, we will end this session. In the next session, we have to discuss about various operations that can be performed on arrays. So thank you for now.